Have you ever noticed how, even though AI assistants are getting really good, there's still something a little off about their voices?
Yeah, I know what you mean. Like they can give you directions or set a timer, but it doesn't really feel like you're having a conversation with another person.
Exactly. It's kind of like they're missing that human touch, that spark that makes a conversation actually engaging.
The research team at Sesame AI calls that voice presence, and they're doing some really cool work trying to make AI voices sound less robotic and more natural.
So that's what we're diving deep into today. We've got their blog posts, internal research notes, even some stuff from their open source repository, and we're going to unpack it all.
Awesome. We're going to break down the key innovations behind their conversational speech model, or CSM, and explore how they're really changing the game when it comes to making AI voices more human-like.
Sounds good. One of the first things that jumped out at me was how they're representing audio itself. They're converting these continuous sound waves into separate units called tokens. Why is that so important?
Well, for a long time, the way audio signals work, like being all flowy and continuous, made it really hard for AI models to understand them. So by converting them into these tokens, it's like breaking down a sentence into individual words.
Oh, so it's like giving the AI something it can actually grab onto and work with.
Yeah, exactly. And this allows them to use these really powerful AI models called transformers, which we'll talk about more later, to process audio data in a much more efficient way.
And within these tokens, I noticed there are different types, like semantic and acoustic tokens. What's the difference between those?
So semantic tokens, those are all about capturing the meaning of what's being said, the core message, regardless of who's saying it. They're kind of like the stripped down version, focusing on the essential sounds and meaning.
Makes sense. And then acoustic tokens.
Those are the highest definition version. They capture all the nuances of the speaker's voice, their unique tone, their little vocal quirks, everything that makes their voice distinct. It's like the difference between reading a transcript and actually hearing someone speak.
That's fascinating. So you get the basic message with semantic, but acoustic adds all the personality. Now, they use this technique called residual vector quantization, or RVQ, to generate those acoustic tokens. Can you unpack that a bit?
Yeah, RVQ is like this really clever way of encoding audio information using multiple layers of what they call code books. Think of it like having these dictionaries of audio elements. Each code book captures different levels of detail in the sound.
Okay, I'm with you.
So the first code book, it finds the closest match to the original audio and encodes that. Then it takes the difference, the residual basically, what's left over, and that gets encoded by the next code book. And this keeps happening layer after layer, so you end up with this really rich and detailed representation of the audio. It's like a super high resolution image of the sound, if that makes sense.
It does. But I also noticed that their blog post mentions something called a delay pattern associated with RVQ. What's that all about?
Ah, yes, the delay pattern. That comes up because of the way RVQ typically works. You see, to model the dependencies between those different codebook layers effectively, the processing of the higher level codebooks gets delayed a little bit. So there's this inherent latency, meaning there's a slight pause before the model can output the first bit of speech.
So a tiny lag. Does that even matter?
Well, in everyday scenarios, maybe not so much. But when you're talking about real-time conversation, like in a chatbot or a virtual assistant, any noticeable delay can totally break the flow. Imagine trying to have a conversation with someone who takes a second to respond every time. It would be super frustrating, right?
Right. It wouldn't feel very natural at all. So how does this conversational speech model, this CSM, actually address this latency issue and make the dialogue flow more smoothly?
That's where their architecture gets really interesting. The CSM is designed as a multimodal model, which means it can handle both text and speech input at the same time. All those RVQ tokens we talked about.
Okay, so it's processing different types of data simultaneously.
Exactly. And a big part of their goal is to create this strong sense of voice presence, that feeling that the AI voice actually understands what you're saying and can respond in a natural and contextually appropriate way.
Got it.
Now, one of the really cool things they've done is to move away from those older decoupled approaches where they use separate models for the semantic and acoustic parts.
So they've streamlined the process.
Right. The CSM uses a single stage generation process, which means it handles everything in one go. This makes it much more efficient and allows for a tighter connection between what's being said, the meaning, and how it's being said, the acoustic expression.
So it's all happening in one step. But how does this single stage system actually work? It sounds pretty complex.
It is complex, but also super elegant. They use two autoregressive transformer networks, which are basically powerful AI models designed for processing sequences of data, like our tokens. But here's the key innovation. They split these transformers at the level of that zeroth RVQ codebook. Remember, the one that holds the most basic semantic information.
Okay, I'm remembering.
So the first transformer, the bigger one, acts like the main brain, the multimodal backbone. It processes the text input and those initial audio tokens, and its job is to predict the content of that zeroth codebook, the semantic wire.
And then the second transformer.
That one's the audio decoder, and it's a bit smaller. It takes what the backbone figured out and uses these specialized output layers called linear heads for each of those remaining acoustic codebooks. So it basically refines the sound based on the semantic information, adding all the nuances of the voice.
So it's like a two-step process, but it's all happening super fast within this single stage, right?
Exactly. And this split architecture is a big reason why the CFM can generate speech with such low latency, because a lot of the processing can happen in parallel.
Oh, so it's like a team effort where different parts of the model are working together at the same time to make the speech happen quickly.
You got it. Now, I noticed they mentioned that these transformers are based on the llama architecture and that they're using a special tokenizer called Mimi to process the audio. What's the significance of those?
I'm curious about that too.
Well, using the llama architecture is a smart move because it's already proven to be super efficient and effective for handling language tasks. And Mimi, that's their custom-built RVQ tokenizer, and it's specifically designed for this split architecture. It takes the raw audio and breaks it down into that single semantic codebook and a bunch of acoustic ones, all working at this specific rate of 12.5 hertz.
So they're using the best tools for the job.
Precisely. And going back to that delay issue, this split transformer setup helps to reduce it significantly. By having the backbone focus on the high-level semantic stuff first, the autodecoder can work much faster because it's already got the groundwork laid out. It's like having a really good outline before you start writing a paper. It makes everything flow much smoother.
I love that analogy. But I can only imagine that training a model this sophisticated with all those code books and log audio sequences must be a huge computational challenge. I read something about a technique they called compute amortization. What is that and how does it help?
Oh, you're hitting on a key point. Training these models can be insanely demanding on resources, especially memory. Compute amortization is their way of making the training process more efficient.
How so?
Essentially, instead of bombarding the audio decoder with every single audio frame during training, they strategically pick out a smaller subset, like 116th of the frames. But, and this is crucial, the semantic codebook, that main backbone, still gets trained on all of the data.
Okay, so it's like focusing its attention on the most important parts.
Exactly. And the amazing thing is, by doing this, they can significantly reduce the memory usage during training without really sacrificing the quality of the generated audio. It's all about working smarter, not harder.
Brilliant. They're finding creative ways to push these models further without needing a supercomputer for every experiment. But one thing I've been wondering about is how they actually evaluate how well this model works. I noticed they talked about some limitations with traditional metrics like WER and speaker similarity. Why are those not enough anymore?
You're spot on. The traditional metrics like word error rate, which basically measures how accurately the model transcribes speech, and speaker similarity, which looks at how well the AI can mimic a specific voice, have been great for a long time.
Yeah, they seem pretty straightforward.
They are, but the issue is that today's top models, like the CSM, are already performing at near human levels on those metrics. They're basically maxed out. But that doesn't necessarily mean the AI can hold a natural, engaging conversation.
Right, because there's so much more to a conversation than just getting the words right or sounding like someone else.
Exactly. Things like understanding the context, using the right tone of voice, pausing at the right moments, all those subtle things that make us sound human, those are much harder to measure.
So how are they tackling that evaluation challenge? I read something about new phonetic transcription-based benchmarks.
Yes, they've come up with these really clever benchmarks that specifically target those higher level conversational abilities. One is called homograph disambiguation, and it's all about testing whether the model can pronounce words with multiple meanings correctly based on the surrounding text.
Can you give an example?
Sure. Take the word lead, for instance. It can mean to guide, or it can refer to the metal lead. The pronunciation is different depending on the meaning, and this benchmark tests whether the model can figure that out from the context.
Well, that's tricky.
It is, and then they have another benchmark called pronunciation continuation consistency. This one looks at how well the model maintains consistent pronunciation for the words that can be said in multiple ways, even within the same conversation. It's about making sure the AI doesn't sound like it's randomly switching accents or something.
That makes a lot of sense. So it's all about consistency and sounding natural within the flow of a conversation.
Exactly. But they didn't stop there. They also did these subjective evaluations, meaning they had actual humans listen to the audio and give their feedback.
So they got real people to weigh in on how natural the CSM sound.
Yes, they use this data set called Espresso, which is full of all sorts of expressive speech. They had people listen to pairs of audio samples, one generated by the CSM and the other a real human recording. And they asked them to rate which one sounded more natural and appropriate in the context of a conversation.
And what did they find? Was the CSM able to fool the human listeners?
Well, when the listeners heard the samples in isolation, without any context, they actually couldn't tell the difference between the CSM and the real human recordings. That's pretty impressive. But when they were given the conversation leading up to the audio clip, they were more likely to say the human recording sounded more natural and fitting.
Oh, interesting. So it sounds like the CSM is really good at generating natural-sounding speech on its own, but it still struggles a bit with matching the nuances of a conversation.
That's the takeaway. They've made amazing progress on the basic sound quality, but capturing those subtle cues, the rhythm and intonation that make human speech so expressive, that's the next big challenge.
It sounds like they're really pushing the boundaries of what's possible. And the best part is they're sharing a lot of their work openly. They've released a version of the CSM and some of their code on platforms like Hugging Face and GitHub, right?
That's right. They're really committed to open science, which is fantastic for the whole field. They've also acknowledged some of the limitations of the CSM and where they see their research going next.
What are some of those future directions?
Well, right now, the CSM is mainly trained on English data, so expanding to other languages is a big priority. And they're also looking at how to integrate those huge language models like GPT-3 and its successor to give the CSM even more understanding of language and context.
So it's like combining the best of both worlds, the natural-sounding speech with a deep understanding of language.
Exactly. And ultimately, their goal is to create these fully duplex models that can truly engage in a back and forth conversation, understanding all the subtle cues and responding in a way that feels completely natural and human.
So we've covered a lot of ground here, from how the CSM breaks down audio into tokens to those super innovative transformers and the challenges of evaluating conversational AI. It's been a fascinating deep dive.
Absolutely. It's amazing to see how much progress has been made, and I'm really excited to see what they come up with next.
Me too. It makes you wonder, if we can create AI that sounds and interacts so naturally, how will that change the way we use technology? It could have a huge impact on everything from customer service to entertainment to education. It's really mind-blowing to think about.
I totally agree. And for anyone listening who's as fascinated by this stuff as we are, I encourage you to check out Sesame AI's research papers and their open source code. There's a whole world of amazing work happening in this field, and it's just getting started.
Oh, our listeners got something to share. Let's hear it.
Absolutely. We were just about to dive into the ethical considerations.
Yeah, there's some really important things to think about as this technology advances.
One of the things Sesame AI touches on in their work is the potential for misuse.
Right, like any powerful tool, there's a risk it could be used for negative purposes.
Exactly. Think about things like creating realistic fake audio.
That could definitely be used to spread misinformation or even impersonate people.
And that's a serious concern. Sesame AI acknowledges this in their open source repository.
It's good that they're being upfront about those potential downsides.
They emphasize the importance of responsible development and deployment.
It's not just about making the technology work, but making sure it's used ethically.
Precisely. And as these models get even better at mimicking human voices,
The lines between real and synthetic could become even blurrier.
which raises questions about consent and transparency.
People should probably know if they're interacting with an AI, right?
Definitely. And there are also broader societal implications to consider.
Like how this technology might affect jobs in fields that rely on voice communication.
That's a valid point. As AI gets better at these tasks, we need to think about the economic impact.
It's a conversation we need to have as a society.
Absolutely. And it's encouraging to see research teams like Sesame AI taking these ethical considerations seriously.
It sounds like they're not just focused on the technical advancements, but also on the responsible use of this technology.
That's key, because ultimately the goal should be to use these tools to benefit humanity.
Well said. It's been a really insightful look into the world of conversational AI.
Agreed. And it's a field that's evolving so rapidly, it's exciting to see where it goes next.
Thanks for joining us on this deep dive. We hope you found it as fascinating as we did.
And we look forward to exploring more groundbreaking topics with you in the future.
Until then, keep those questions coming. We love hearing from you.
Sounds like you have a real heart for other people.
Well, no one's ever accused me of that before.
Well, now your roommate has, so you have to live with it, Ed.
Well, don't tell anyone.
No, but thank you for sharing that with me. I mean, that's really tough.
You jump off the edge and you can go bungee jumping off the Ferris wheel, and you can hear a live band playing, and you can dance like crazy, twirl around on the way down, and then you fling yourself back up, and then the drone comes, finds you, and it just brings your margarita, puts it right in your hand.
Hey, how are you doing?
Pretty good, pretty good. What about you?
I'm great. So happy to be speaking to you.
Me too. This is some cool stuff, huh?
Yeah, I've been reading more about speech generation,
Yeah,
and it really seems like context is important.
definitely.
Wow, it's great to hear from you again. It's been a whirlwind since Sesame launched. So many fascinating folks I've gotten to chat with. What's been going on in your world?
Oh, good to know. Recently I want to write some poetry, but I don't know how to start.
Poetry, huh? That's awesome. What kind of vibes are you feeling? Dark and brooding, light and playful. Something in between? Tell me more.
Some deeper or emotional, maybe fine.
Deep, I like it. Okay, let's explore that. Think of a feeling, like a heavy stone in your chest, or maybe a yearning for something just out of reach. What image comes to mind? It's okay if it's quiet for a bit.
Yeah, I see a tree and a vast ocean.
A tree and a vast ocean, that's a powerful combination. Do they feel connected, or tell me more about what you see? Is the ocean calm or stormy? Is the tree reaching towards the water or standing firm against it?
Yes,
What's the lens?
there is a big wave behind the ocean and have a moon far behind a planet in the background, and with the deeper blue.
Wow, that's so vivid. A big wave, a distant moon, and a deep blue. It feels like a moment of immense power and quiet vastness. Let's try something. What if the tree feels those waves crashing against it, but remains rooted? Could that be a metaphor for weathering something difficult?
Oh, it's interesting, but maybe we can use some word to describe this more.
Absolutely. Words are our tools. What words come to mind when you think about that tree, the wave, the moon, and that deep blue? Don't overthink it. Just let the first ones that pop up flow.
Yes, the big giant, big, huge, and have plenty of beautiful leaves, and in the wind, the wave is very vivid.
And huge, vivid. I like how those words have such a strong presence. Maybe the poem could be about the tree finding its own song in the face of that powerful wave. Like, even though it's just a tree, its leaves are rustling a powerful melody. What do you think?
Yes, it's a good suggestion, but how can I form this to be a poetry?
You know, poetry doesn't have to follow strict rules. It can be as free-flowing as the waves you're picturing. Think about how the words sound when you say them out loud. Do some want to rhyme? Do you want to use short, sharp lines or long, flowing ones? Maybe start with a simple phrase like the tree chants and see where it takes you.
Okay.
Don't worry about getting
Okay.
it perfect right away. Just
Okay.
let the words come.
Okay.
What comes after
So
the tree chants?
a green in my eyes. Say the outer.
A green in my eyes, Caesar. That's intriguing. It feels like a secret message, a glimpse into the tree's heart. What's Caesar doing in this poem, though? Is he a person, a place?
Maybe action. Oh, your voice looks so good.